Recording first. There we go. All right, so everything is getting recorded from this point on. All right, so I hope you guys got a chance to kind of review the floating point number stuff because we spent a good portion of last week on, well, we spent one entire class on exam one. If you have any questions individually, you can always ask me, during the office hour or just, send an email to me. I have not yet started to grade the exam yet, so I will get started on that soon. But if you do have a question about your specific answer or something like that, you can always just contact me and I can explain the answer, explain how to approach and so on. So with that said, we are moving on and continuing with double precision floating point numbers. Just to remind you what it is, let me get to this page here. This is a Wikipedia page, and I think it gives you a really good pictorial representation of a floating point number format. So basically, you have 64 bits. Okay, there are 64 bits in a double precision floating point number, and that name should automatically prompt you to go like, so if there's a double, does that mean there's a single? Yes, there actually is a single precision floating point number, and it is not being used too often anymore because it doesn't have enough precision for a lot of stuff. So what is interesting is, as we are talking about this topic in this class, CISP310, which is object-oriented programming, Ryan is starting to, teach that class using a graphical engine, and the students were doing fractal graphics, and they ran into a problem. They ran into the problem of pixelization. When you zoom in too much, then the detail is no longer fine. And that is a problem related to what we are talking about here, because in that class they are using single, which is a single precision floating point number, which in C++ is float. The type is called float. What we are talking about here is the type that we call double. Um, so anyway, at some point I can explain why they have that problem in CISP 400. But for now, we're going to get back to this and just to explain, how to use all of these bits. The most significant bit, which is bit 63, that is just sign itself. In other words, it is basically specifying whether the quantity is positive or negative. So it doesn't do anything else. There is no signed representation here. So 2's complement does not apply. We do not have any signed representation. So the next portion, which is the green portion, that's going from bit 52 to bit 62. There are 11 bits. So those 11 bits should be seen as an unsigned integer. And that unsigned integer is what they call E in this notation, in the Wikipedia notation. It is simply called E for exponent. It is the exponent of 2. However, it is biased. Okay, there's a biased amount of 1023. So that means if E itself is actually 0, if you have the green portion here being all zeros, then the exponent of 2 is actually negative 1023 because of the bias of 1023. Is that concept okay? Okay, so in order to have an actual exponent of 0, you need E to be 1023 itself. Because 1023 minus 1023 is exactly 0. Okay, so that's kind of interesting. The pink portion, which is kind of salmon pink, that is the fractional part of the mantissa. So I explained to you what a mantissa is. It really is a coefficient that is already normalized. So the coefficient has to be between 1 and up to, but excluding the base itself. Now, if we're talking about in base 2, that means it cannot be exactly 2. It has to be less than 2, or what we know as 2. So in binary, it simply means that the mantissa itself has to be 1 point blah, 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 a bunch of binary digits after that. Well, but if it's always 1 point something, why do you want to waste 1 bit to represent the 1 of the 1 point? So that's why that 1 point is never represented explicitly. But that's why you see this 1 here as a constant. It is always there. The rest of the bits are the fractional part of the mantissa. And if you look at the sigma notation, when I equals to 1, then b subscript b 51 times 2 to the power of -1 is specifying how many halves we have. So one way to look into the sigma notation to find out what it's trying to tell you is to substitute actual values into I. So I would start with I equals to 1, find out where it starts, and then substitute I equals to 52 and find out when it ends. Then you will find out that a different notation is this notation here. It's 1 point and then B51 for the digit right to the immediately to the right hand side of the point, B50, which is 2 digits to the right hand side of the point, and so on. And then B0 is all the way to this side. In other words, B0 is going to specify a very, very small quantity when it comes to contributing to the mantissa. Are we good so far? So that's basically what we talked about in, I think, on last Monday. So what we'll do today is to think about how to do conversion, because it is unlikely that you are going to specify a value using the double notation, because you have to do the conversion, right? You have to specify everything in zeros and ones. Instead, it is much more likely that you're going to specify a quantity using base 10 scientific notation. Are we good so far? All right. So now the question is, how do you convert from base 10 scientific notation to a base 2 basically scientific notation as well? Because you have the mantissa, you have the exponent of 2, and then you have this sign thing that's just hanging out all by itself. So we are still talking about scientific notation in the sense that you have a coefficient times the base raised to the power of something, some integer. And that would still be quote unquote scientific notation. Any questions before we proceed? Any questions about the terms that I have described up to this point? Okay, if there are no questions, then we're going to take a look at an example. I will also make that available to you using Google Drive. So if you have a computer in front of you, or if you want to follow along with the equations, you can go to the shared folder, which is at the beginning at the top of the modules of the Canvas shell for this class. So you can go there first, and then I'll follow up. Okay, so you should get to this folder if you follow that link. I'm going to create a new spreadsheet. There's one already, but I want to create a new one, just for this class, because I want to explain this, interactively because otherwise I can just replay the lecture on last Tuesday for the other class, because it will be the same content. But that's not going to be very interactive, which defeats the whole purpose of an in-person class. So I'm going to do this interactively, so you guys have a chance to ask questions as we do all the conversion stuff. So I'm going to create this document. Don't try to get to it yet, because I have to rename it first. So let's call this based on the value that I'm going to convert. So I'm going to use the speed of light. Well, let's see, would that be a good one to use? Because I want something that's large enough that it's not going to be an easy conversion. So let's try something bigger. Okay, so I'm going to try 1.23 times 10 to the power of, we can do negative exponent first. So times 10 to the power of 45, negative 45. That should be a pretty small value. So that's the name. If you go to the Google Drive right now, you should be able to see this as one of the files. It is named literally as 1.23e negative 45. So if you do find it, you can follow along with the equations, because sometimes when I type a little bit faster than you guys can write down or to comment. So if you just kind of get to the document all by yourself, then you can actually have more time to look into how the equations are set up. So I can see many of you are already in this document. Excellent. All right. So we're going to start with this particular value, which is exactly 1.23 e negative 45. Now, when you type something like this on a calculator, you have to be very careful, because a lot of calculators would look at the lowercase e key as natural log to the power of something. So you have to differentiate that e from the e notation of in a double or floating point notation, and that one is brand dependent. So if you have a TI calculator, the actual key to specify the exponent of 10 may be EEP or EE or EXP. It depends on whether it's Sharp or Casio or TI. They all have a slightly different notation. Just be careful when you enter that. All right, so a spreadsheet doesn't have a problem with that. I can actually just do this. So now the first thing is, how do I change the exponent of 10? Because the idea is to increase the exponent of 10 to 0 by changing the other two parts, which is the coefficient part as well as the exponent of 2. So there's no exponent of 2 right here. Let me explain what I mean by that. Um, and that is probably better done using Zerno. So let me move Zerno into your view first, and then I'll give you the actual equation. All right. Okay, so I think it's all set up. Oh, no, I have to run the script first. Let me run that script. Which is fixed stylus. Here we go. Okay, got it. All right. So the value that we want to represent is 1.23 times 10 to the power of negative 45. Okay? And, okay, so you look at this and go like, okay, what is the big deal here? Well, the big deal is I also want the conversion process not to make use of log, not to make use of floating point number representation itself, not to use exponent or power. I want this to be only using integer arithmetics. So we are talking about addition, subtraction, multiplication, division. We can also use bit shift operations. Okay, so by the time we get to that point, I can explain what I mean by bit shift operations. So the first problem is, I think we're going to have a problem just to represent 1.23 times 10 to the power of negative 5. So initially, it is just a string. Okay, so we want to start this as a string, which is just 1, literally 0.23, lowercase e, negative 4, 5. So we have to break up the string into the portions first. We have to break that string into, okay, this side 1.23 is the mantissa, E is basically just a marker to basically say whatever is on the right-hand side specifies the exponent of 10 in this case, and then we have to parse negative 45 as the value of negative 45. So that's a lot of trouble, okay? Um, when I first started to teach this class, one of the assignment was to write a parser to convert the string into all the various parts. I decided not to do that anymore because the string conversion part is not really related to what this class is about. So I will give you that code already. Okay, but remember, one of the constraints is I do not want to represent. I don't want a double representation. I don't want to use the double type or the float type in the entire program, which means the mantissa all by itself is a problem already because the mantissa is 1.23 in this case. So how am I going to solve that problem when everything is supposed to be represented using integers, signed or unsigned? So there's a little trick to this, okay? So the little trick to this is to look at this and go like, I can, instead of writing 1.23, I can now say 123. But this equality means, oh, but this is bad, Tech, because you just multiplied the mantissa by 100. So it's no longer, quote unquote, technically a mantissa because it is no longer within the range of a normalized mantissa. But I'm still going to call that the mantissa. We'll call this the non-normalized mantissa. Or you can just look at it as a coefficient. So what we can do instead is to say, but we know what to deal with, how to make it 1.23 again. I just need to multiply 123 by 10 to the power of -2, then it becomes 1.23 again. Okay, first of all, let me pause. Does that make sense from the mathematical perspective? Because if it does not, then we have a different issue to deal with. So is everybody comfortable with the math part of this? Yes? Okay, because that's exponent calculation, and then the rest would still be times 10 to the power of -45. Then go like, I bet you we can group the two 10 to the power of something together, right? Because they're both powers of 10, and if you have a bunch of powers of 10 in a multiplication, they can be combined. So how do we combine the two powers of 10? Go ahead. Add them together? Exactly. So we have -2 plus -45, which is -47. Okay? So now we have 123 times 10 to the power of -47. Does that make sense? Are we good so far? So I can have a structure in C where there's an integer that represents the 123, which is the coefficient, and then I have another signed integer to represent the power of 10, which in this case is -47. Problem solved. Okay, I can at least represent this without the use of a double nor a float. Are we good? All right. So then the next question is, how are we going to change the power of 10 from -47 to something else? That would be the next question. But before we answer that question, I'm going to add something here. I'm going to add one more component to the multiplication, and I'm just going to say 2 to the power of 0 is 1. I can always multiply that without changing the value of the rest of the expression. Does that make sense? Okay? Okay. So how do we change the power of 10 so at least it goes up to -46? Well, if I bump the exponent of 10 by 1, I should change the coefficient how? How should I change the coefficient if I decide to change the power of 10 and bump it up by 1 in order to preserve the same value? Okay, bumping up the power of 10 by 1 is equivalent to what kind of change to the value of the entire thing? It's, okay, bumping up the power of 10 by 1 is multiplying by 10. So in order to compensate, we have to divide the coefficient by 10. Does that make sense? In other words, okay, I'm going to say, okay, so if we have a division by 10 here, then we can afford to bump the exponent of 10 up by 1. Does that make sense? So mathematically, this makes sense. But we have a problem. The problem is this division, in order for this equality to hold, this division has to be a floating point division, has to be a double division, because an integer division, what is the result of 123 as an integer using integer division and divided by 10? What is that going to give you? It's going to give you 12, right? Because the fractional part is lost, completely lost. So we look at that and go like, well, is that loss okay? I mean, is it acceptable? Is that margin of error okay? And most of you are turning your head already because it is a pretty bad error, okay? Because when you look at 123 divided by 10, an integer division is really just a regular division, but you put a floor on the outside of the entire thing. This is 12. But if you take out the floor symbol, this is 12.3. So what is the error? The error is -0.3 divided by 12.3. Because 12.3 is supposed to be the actual result, but when you look at the difference between 12, which is what we're getting, and the expected result, which is 12.3, the error is -0.3. In other words, the actual result, the result from the integer division, is a bit smaller than what it is supposed to be. Are we good so far? All right. So now I'm going to look at this and go like, I wonder what we can do to kind of, at least alleviate this problem, okay? Because, I know, there's always going to be a division by 10 somewhere, and we're going to lose some precision. But I want to make it not as obvious, right? So let me give you a proposal here, okay? So I can now say, what about 123 times, I'm just going to say 16 here, this whole thing divided by 10, look at the floor of that, and then look at 123 times 16, the whole thing divided by 10. Now, obviously, the floor is still going to cut off some unit, right? Cut off some value. The question is, what is the margin of error in this case? What is the actual amount of error in this case? Well, this is where a spreadsheet is going to come in handy. So I'm going to switch to the spreadsheet on the projector, just so that I can play with this and you can see what the value turns out to be. So I'm going to add sheet 2, kind of like a worksheet here. So I would just do the calculation. So in this case, we have 123 times 16. Take the floor of this whole thing divided by 10, and then subtract from what it really is, which is 123 times 16, the whole thing divided by 10. So we are looking at negative 0.8 as the error. But the ratio of the error is not quite as bad, because if we want to look at the ratio, then it becomes the actual absolute amount of error divided by what it is supposed to be. So now we have 123 times 16 divided by 10. That is what it's supposed to be. You can see the error is now less than 1%. I think this is quite a bit better compared to before. Is that making any sense? The error is always coming from the division by 10, which means the amount of error is always going to be less than 1. Okay, it's always going to be less than 1, but it can go all the way up to like 0.9. Okay, so the absolute value, which is represented by cell A1 in this case, that's, I cannot control the range of that. Okay, that is always going to be from 0 to 1, excluding 1 itself. But what I can control is what is the proportion of the error from what the value is supposed to be. So I can increase the accuracy by making the numerator as big as possible before the division, right? In other words, in this case, if you look at the equation, I'm using times 16. What if this is times 256? Don't you think the error is going to be less in terms of proportion? What if it is 65,536? Even better, right? So we want to make it as large as possible. We want to maximize the numerator before we perform the division. Is that okay? So our first question is, how many times can I double 123 before we run out of digits in a unsigned integer? And then we have to say, okay, gotta stop here, because if I multiply this one more time by 2, I cannot put that value into a 32, into a 64-bit integer or 52-bit integer or whatever width we want to use. Okay, is that making any sense? Okay, so in this class, for demonstration purposes, I am not going to go all the way to 64-bit. One, because it is just going to be insanely long, and two, it is also because a spreadsheet cannot represent exact values beyond a certain range. So I'm not going to do it. I'm going to assume that we are using only 32 bits for the unsigned integer, being responsible for the coefficient. All right, so I'm going to use another row here, and this is going to be the coefficient. This is going to be exponent of 10, and this is going to be exponent of 0. The exponent of 0 is going to be 0 to begin with, because I don't want it to be interfering with anything just yet. The exponent of 10 in this case is going to be negative 47, and the coefficient is 123 to begin with. In other words, if I look at row 3 and I ask, what is the value of 123, which is the coefficient, times 10 to the power of negative 47 times 2 to the power of 0, I should get back 1.23 times 10 to the power of negative 45. right? You guys are all nodding, but nobody's going like, tech, prove it. Okay, which is what you're supposed to be doing. Okay, you always want to question. It's like, yeah, what you said seems to make sense, but is it really the case? Well, let's double check. So we're going to say the coefficient, which is column A, times 10 to the power of negative 47, which is column B, times 2 to the power of column C, and it gives me a 0. It's like, what? Well, that's because of a formatting thing. Because normally this is not formatted to use scientific notation. So what we need to do is to say, okay, for the entire column D, change that to use scientific notation. And then we get it back. All right, so now we know we have preserved the value. So the next thing I'm going to do is to try to double it, right? So I'm going to double the coefficient from 123 to 246 by doubling it, right? So we just say, all right, let's double it. Whatever we have before times 2. So when we do that, I'm not going to change the exponent of 10. It's still going to be preserved. But we do have to change the exponent of 2 if we want to preserve exactly the same value. Does that make sense? Because if I don't make any changes, okay, so let's just say that this is continuing to be 0, then the value being represented is doubling what it used to be, which is not what I really intended to do because I want it to be preserved. So what should I do on row 4 in order to keep the value being represented? Divided by 2, but I can't divide it by 2. I can only mess around with the 3 cells. This one is fixed because I want to double it. I can mess around with this one, or I can mess around with this one.
Divided by 2 to the power of 1. Use exponent of 2?
Negative 1.
Negative 1.
Negative 1. So you got the right idea. We have to adjust the exponent of 2, but we have to go the opposite way. We have to make it negative 1 in order to have the same effect as dividing the whole thing by 2.
Doubling one side instead of half the other.
Exactly, because we want equality between the rows. The rows are supposed to be representing the same value. So if you double one side of one component, you have to somehow have the same effect as having somewhere else within the equation. Okay, so now we say, okay, 0 is not going to work, but using this value minus 1 does. Do you see how column D is now exactly the same? So we're good here, okay? So now we can look at these and we say, okay, how far can we go, before we run out of bits, right? So you can see, how all of these rows, they all basically end up, the product ends up to be, which is in column D, they're all identical. I have not lost anything. But the question is, at some point, I will no longer be able to represent the value of column A in a, I'm using 32-bit in this case, just because it's easier to get to that point. But at some point, I'm going to run out of digits in a 32-bit unsigned integer. The question is, at which point? So we're going to use another column to check to see if we have run out of digits based on what we have in column A. Is that okay so far? Does everybody understand what I'm about to do? Because I want to know when I need to stop doubling. All right, to do that, I need comparison. So what I need to do is to simply ask the question of, is this value less than the maximum integer that I can represent, in this case, using 32 bits? In your assignment, which is going to be on this Thursday, you are going to be working with 64-bit, but in the example, I'm only using 32-bit simply because otherwise it just gets a lot longer, and plus the spreadsheet cannot exactly represent 64-bit unsigned integers, which is a limitation. So given that we have a 32-bit unsigned integer, how do you figure out the maximum value that it can represent?
2 to the 32.
Minus 1. Yep. Don't forget the minus 1 because we started with 0. So 0 itself is taking one of the spots. So the maximum value is 2 to the power of 32, the whole thing minus 1. Okay, so we'll just ask the question, which is, We are looking at 2 to the power 32, the whole thing minus 1. And, okay, is it surprising to you that 123 can be represented by a 32-bit unsigned integer? That should not be surprising at all. So without even using this math here, is there a way to kind of eyeball this whole thing and find out at which point um, the value of column A is going to be too big? So let me repeat the trick. I think I might have mentioned it in this class, but maybe I have mentioned it in the other class. 10 to the power of 3 is 1,000. We know that. 2 to the power of 1,024, excuse me, 2 to the power of 10 is 1,024, right? Well, let's count. 2, 4, 6, 8, 16, 32, 64, 128, 256. And if you keep going, by the time you get to 2 to the power of 10, you have 1,024. So you go like, okay, 1,024 and 1,000, they're kind of close. For estimation purposes, they're close enough. So what we do is now say, if you have 32 bits, what would be the largest value, approximately the largest value you can represent? So you say 2 to the power of 32, which means it has 2 to the power of 10, that whole thing to the power of 3. Okay, let me use Zerno to write this down because I think it's better to be more visual in this case. I'm going to put it on a page before this page here because this is just kind of scratch paper. Okay, so we have 2 to the power of 32, which is 2 to the power of 10, the whole thing to the power of 3, times 2 to the power of 2. And we look at this and go like, yeah, that is approximately 10 to the power of 3, that whole thing to the power of 3, times 2 to the power of 2. And that equals exactly to 10 to the power of 9 times 4, which we know as 4 billion. Is that okay? So the largest value that a 32-bit unsigned integer can represent is about what we call 4 billion in base 10. Is that okay? This trick is helpful because it gives you a really quick way to do the conversion. If you give me the number of bits, I can give you the rough range of values that it can represent. Is that okay? Does everybody understand this math here? So that means in the spreadsheet, I'm looking for something that's close to 4 billion because then it's going to run out. So let me switch back to the spreadsheet here. So that means column A probably should be using the comma, to separate to group the three digits at one, to group the base 10 digits by groups of 3. Okay, that's the best way to put it. But instead of doing that, I'm just going to use the condition, and I'm just going to say, well, tell me when it is too much. So far it's still okay. So we'll continue to double a few more times. Still looks good. And now it's not. So if you look at this value over here, this is 4 billion something. And because the approximation is not exact, this turns out to be still representable using 32 bits. Oops. And then this one is not representable using 32-bit anymore. Are we good so far? All right. Then what do we do? Well, I think we're ready for division. Because remember, why are we doing all this stuff here? Because we want in the division, we want the numerator, or if you want to use division term, we want the dividend to be as large as possible, right? This is, in this context, this is as large as possible. I cannot double that anymore. So now I have to do a division by 10. Okay. But we have another problem. The other problem that we have is every single time we do a division by 10 using integer division, okay, I'm waiting for the screen to update. So every time we do a division and we take the floor of the actual division, what is the sign of the error? So we now know that the numerator or the dividend can be really, really large, which makes the error a really small amount. But what about the sign of the error? Are we changing the sign of the error at all? Or are they all going in one direction? Let me ask that question one more time. Now we are dealing with a gigantic value, right? Okay, so the numerator is huge, and we are dividing it by 10. Okay, let me see if I can do this because I want to I want to show you exactly what I mean by that. So let me get here, and then we'll do a screenshot with exactly that value. I'm doing this in a very lazy way. All right, and then we can now paste that thing here twice, okay? In fact, okay, let me undo this and put it here. And then both of these time, I'm going to divide it by 10. You don't have to actually do the math because this is basically just me asking you a question. So this is what we're getting, and this is the exact value. So when we do the subtraction here, what is going to be the sign of the error? We know the error is going to be small compared to the actual, the percentage of the error is small, but what about the sign of the error? It's always going to be negative, right? This is always going to be negative. The reason why is really simple, because the floor of a value is always less than or equal to the value that is being floored, right? So this means, if I need to divide by 10, in this case, many, many times, like 40 something times, that means, I'm going to accumulate errors, but they're all going in the same direction, which is a problem. What kind of a problem is this? It's kind of like driving a car with an alignment issue. Okay, so the car is always going to try to, you know, lean to one side, like let's say the left-hand side. So eventually, you're going to be out of your lane, which is not good. Okay, so we want the error to be sometimes negative, sometimes positive, and other times negative. So it would somewhat average out. Does that make sense? So instead of floor, we want rounding. That's basically what I'm looking for. Is I want rounding instead of the floor. But the problem is, I want to do everything using integer math. I don't want to use the floor math function. I don't want to use the round math function. I want to do everything just using integer math. So now we have to do some observation. So I make this claim here. So I make the claim the round of x is the same as the floor of x plus zero point 0.5. So I make this claim. You go like, okay, I'm not sure exactly how that works. So what do you do when you look at something like this, kind of abstract, and I claim that it's going to work? So what are you going to do? What are you going to do? Hmm? Plug in numbers. Okay, so plug in numbers where it might make a difference. Okay, so don't plug in numbers like just 1 and then 2 and then 3 because they're all integers. Okay, so they all kind of work the same way. You want to plug in something that's right at the border of, okay, this is the value that we step up to the next integer in a round, and we want to make sure that the other way is going to do the same thing. So we're going to test a few values. So the first one is 1.2. Okay, is that the same thing as 1.2 plus 0.5, the floor? Well, is that the same thing as 1.7, the floor, which is 2? But wait, no, 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 I take it back. Tick, tick, tick. Which is 1. There we go. Does that make sense? Is the round of 1.2 1? Yeah, it seems to make sense, right? Okay, so now we try to go for something that's also obvious, which is, let's try 1.7. So now we have 1.7 plus 0.5 equals to what? 2.2. The floor of that is 2. Is that working out for you? Okay. So now we go for something that's like, okay, if there's something that's not going to work, it's going to be this value because it is right between rounding down and rounding up. This is the value that will tell us whether this is going to work or not.
Other question, where's the 0.5 come from?
Um,
About 1.5?
that's just me thinking that you're
Okay.
adding 0.5 to the value that you want to round, but instead you're adding it to the value and then take the floor. It's going to be the same thing as rounding. So this time I'll try like 3.5, okay? So now it is 3.5 plus 0.5, and that would be the floor of 4, which is 4 itself. Does that make sense? Is the rounded value of 3.5 4 as an integer? So this one, is by definition, it may not make sense to you because 3.5 is right between the 3 and the 4. So which side should it fall onto? It's kind of like, you know, but most mathematicians will tell you that if you want to do a rounding of 3.5, it should be 4. So now we are relatively comfortable with this notion and go like, okay, so adding zero point 0.5 to the value and then take the floor of that is kind of the same thing as rounding that value to begin with.
It kind of makes sense, but I mean, like, in terms of like if you count to 10, but instead of going from 1 to 10, you go from 0 to 9, kind of 5 is like closer towards that side than it is to the 0.
Mm-hmm.
And even if you have like, so if you replace the 3.5 there with like a 3.6,
Mm-hmm.
and now you have like 3.5, or you have 3.6 plus zero point 0.5, it's like
4.1.
4.1, which goes back to 4
Yep.
because of the floor.
Yep. So it makes sense. Okay. So now the next question is, but tag, this is not going to work because we still have that plus zero point 0.5, and then the value that is being rounded is still going to be a decimal value. It has a fractional part to it. So I'm going to give you um, the more general thing that we're going to do, because what we're rounding is the result of a division by 10. In other words, the actual value x here is an integer. We want to round the value of the quotient of x divided by 10. So if you plug that into this equation, okay, so I'm going to do this step by step. Is that okay? Because I'm just reusing this thing here. Instead of x, I have x divided by 10. I'm taking the rounded value of x divided by 10. So every place where x used to be is now x divided by 10. Is that okay? It is just the application of the equality that I have claimed earlier, except this time we are always rounding the dividend of x divided by 10, or the result of x divided by 10. Is that okay?
It should, yeah.
Okay, so now, using algebra, I can now say, that 0.5 is still a problem. X divided by 10, I can kind of do it using integer math, but we still have the plus zero point 0.5, and I'm explicitly saying that I cannot use float or double. How am I going to represent zero point 0.5? Well, zero point 0.5 is kind of the same thing as a half, right? So I look at this and go like, well, can I consolidate everything to use the same denominator? Sure, right? Because 1/2 is 5 divided by 10. So now I can say it's the same thing as x plus 5, the whole thing divided by 10, and then take the floor of that. Is that okay? Problem solved. Because if you take the floor immediately after a normal division, that is integer division. That's exactly what integer division does, is to take an integer divided by another integer and then take the floor of the actual result of the division. That's integer division. So now this entire thing can be done using integer addition and one integer division. Is that okay? Are we okay with this? All right. Okay. So knowing this trick now, I can now go back to the spreadsheet and emulate doing the same thing on the other side in the spreadsheet. So let me go back to the spreadsheet. There we go. All right. So I'm going to, okay, let me split the screen just for a moment here because I can't, it's not easy to see both sides at the same time. So I'm going to take the last value here. This is the largest Um, okay. This is the largest product of 123 and a power of 2 that is still containable inside a 32-bit unsigned integer. Is that okay? What did I just say?
This is the largest, that's the largest value you can represent without, while it's still being true, meaning it doesn't.
It's still containable inside the 32-bit unsigned integer. Right. Okay. Very good. Because sometimes, I would say one sentence, but it involves a lot of terms. I want to make sure that you guys understand every single term in that sentence. Okay. So that means now I can use another group of 5 columns and say, okay, now we have a new coefficient, and that new coefficient is going to be this thing here, but I'm going to divide it by 10 and using the round technique. So this equation here is going to be taking the floor of taking this value here, add 5 to it, the whole thing divided by 10, and the floor. That really is the same way of what we just saw earlier in Zerno. It's just that this time it is in the form that the spreadsheet understands. We are still taking the floor of the division between a value plus 5 and then the whole thing divided by 10. We're still doing the same thing. It's just represented a little bit differently. So are we good so far? Is everybody making a connection between the equation of F3 and Zerno that we saw earlier? I can show you Zerno right here. Is that okay? Does everybody see how this thing, this is the floor symbol. We're adding 5 to something and then divide the whole thing by 10 and then take the floor of that. And in the spreadsheet, it is just spelled out a little bit differently. Is that okay? All right. Okay, but that means I need to do something about the power of 10. It used to be negative 47 here, but now it cannot be negative 47 anymore because I just divided the coefficient by 10. What should I do? If I divide the coefficient by 10, what should I do to the power of 10 so that when I look at this value here, it would still be the same? Go
You
ahead.
have to add one because taking a 10 away is like taking 1 power of 10 away.
Yep, that's right. So now I'm going to take whatever this value is and say, I can add 1 to it now because I just divided the coefficient by 10, so I can afford to quote unquote multiply the whole thing by 10 in the form of increasing the power of 10 by 1. Are we good? Okay. So we go like, press the enter key, negative 46. Wow. Negative 47 plus 1 is negative 46. This is progress, okay? We're still a long way from the answer, but this is progress. Because we just bumped it up by 1, which means eventually it will get to 0 if we continue to do this, right? Okay. So now we say from the perspective of the power of 2, that has not changed. I still need to use whatever the power of 2 is over here, which is negative 25. And then when I look at the equation of what the entire row is representing, it's still going to be the same as that equation here. So in other words, this time, okay, this is why your Google spreadsheet and spreadsheet program general is useful because it's color coding. So you can see how F3 is our coefficient. It is in orange. G3, which is in purple, is our exponent of 10. And then the exponent of 2 is H3, which is in light blue color. So this gives you an idea of how those 3 components are being used again to come up with the value that they are representing together. Is that okay? All right. So now if I press the enter key, I should get back what? Nope. No. It's giving us the value that the entire thing is trying to represent. So what value have we trying to be representing from the get-go?
Oh, is it general color?
Okay, hold on. Somebody gave me the answer, but I heard 2 people at the same time. So just one at a time. Go ahead. Who wants to go?
23E
1.23 times 10 to the power of negative 45. That's what I should be getting back, okay? Or, in the base, not in the C notation, it is 1.23 e negative 45. So press the enter key. Aha, we got it back. But now the question is, what about the doubling thing? This obviously is going to be containable within 32 bits because I took something that was containable in 32 bit and it divided by 10, which means the quotient has to be representable in 32 bit as well. But the question is, doesn't that mean that we probably need to double this a few times, just so that it's maxed out again, right? Because we want to minimize the error of the division by 10. And I can divide this by 10 right now, but it's not going to minimize the error. So I need to double this a few times to make sure that I'm going to minimize the error. So in this case, I'm going to take this value and say, let's multiply by 2, and the rest is going to be the same. This is going to be the same as before because the power of 10 does not change when I adjust the coefficient by multiplying by 2. But the power of 2 does change. So now I have to say, since I multiplied the coefficient by 2, the power of 2 needs to decrease by 1. Same as before. I mean, this part has not changed from the previous 5 columns. Is that okay? I'm doing exactly the same thing as the first 5 columns, except this time I started off with a much larger value as the coefficient. Yes?
Are we adding an exponent of two? So should it be to the negative 24?
You are right. Okay, I mistyped the plus to a negative. No, this is correct because I'm multiplying coefficient by 2, so I have to divide the rest by 2 by decreasing the exponent of 2. So this is still correct, okay? It's still going in the right direction. Just like these are all going in the opposite direction, in the negative direction, this is going in the negative direction. So we are still good here.
Set up to do in the beginning is to try to maximize, make the
We want to maximize this.
and then the denominator smaller.
Yep. So now I'm gonna go for another row, and so we're still good. We're still good, and we're not good anymore. So what do we do at this point? This is the largest value that we can put into a 32-bit unsigned integer. If I multiply that one more time, it can no longer fit in a 32-bit unsigned integer. So what am I going to do? I have already maximized the dividend of a division or the numerator in a fraction. So what do we do next? Sorry?
Doing the exponent again?
We need to do something about the exponent. But okay, first of all, whose exponent are we going to adjust next?
The 10 again?
Exactly. And what are we doing to the exponent of 10?
Negative 45.
That's right. We are bumping it up. Okay. So I think you guys are getting the idea. Okay, because if I were to play this out entirely, it's going to take up a lot of room. But I think I can just do it like one more time, and you guys will go like, okay, I think we get it. But before I do that, I am going to, this is the value being represented, and this is like fit in u in 32 underscore t, which is the type of unsigned 32-bit integer. So I'm going to reuse the heading of all of these columns. So this way, when you look at the spreadsheet again, you know exactly what is the row of each column. All right, so with that in mind, now I can basically sort of copy and paste, not exactly, but I can sort of. So the header column going to be the same. The first value here is going to be this value here divided by 10, okay? But I don't want to do this, right? Because I need an integer division and I need rounding. So that means I need to do all the other tricks that we were doing before, which is taking the floor of this value plus 5 divided by 10, and then, oh, nope, we need a close here and then another close over here. So we are now division. This is division by 10, but with rounding built into the whole division thing. Okay, that gives me the ability to increase the exponent of 10 by 1 compared to what we had here. So now this exponent of 10 is going to be this guy plus 1. Woohoo! It's negative 45. We're getting closer. And the exponent of 2 cannot change. So this is still going to be the same over here, which is negative 28. And let's check the value. The value is these two are easy. We just need to copy and paste it because it will automatically adjust to which cell they're referencing. So now we now know that yep, we are still preserving the value being represented, even though it's a little bit awkward. It is this particular value times 10 to the power of negative 45 times 2 to the power of negative 28, but we are still getting back to the same value that we want to represent. Is that okay? So from this point, what are we going to do? The same boring stuff. Maximize the coefficient until we cannot fit it anymore. We're still good? We're still good? Not good anymore. Is that okay? Do you want me to repeat this process another 45 times until we get to 0? Or do you guys think that, yeah, I think we're getting the concept? Okay, so from the perspective of the structure of the code to do this, okay, what do you think is going to involve? Okay, so we're going to break down the program, the code a little bit here, just to see, what is involved here. So we're going to go back to the first columns, and I can now move this back all the way to the top, so I don't need to break the screen. In fact, I think I can just kind of zoom out a little bit just to see, oh, okay, that's not enough. I need to zoom up one more time. Okay. So if I just highlight the portion which is from here all the way up to here, if I don't want to do this by hand, and instead I want a program to do this, what type of control structure am I looking into?
A loop.
A loop, very good. A while loop, okay, very good. I was expecting someone to be a smarty pants and going, I can do this with recursion, which you can, but a loop would suffice, okay? All right, so if this is a loop, okay, we already know how we adjusting the coefficient with each iteration, because if we look at this as the trace of a loop, each row is representing the effect of one iteration through the loop. Is that okay? All right, so we know what we're doing. We are doubling the coefficient with each iteration, and we are decreasing the exponent of 2 by 1 for each iteration too. We are not touching the exponent of 10. We're good? The question is, how do I know when I can get out of the loop? Yep.
Check to see if the coefficient, what's the formula? It's right here. Okay. I rescind my thing.
That's okay. That's okay. That's not a problem.
What's 2 to the 30?
Right here.
2 minus 1?
Yep.
When the coefficient isn't representative, is no longer representable by 32.
But how can we tell?
Less than?
So the question is, how do we know this is the last iteration? After this iteration, we should get out. The problem is if you are doing a 32-bit unsigned comparison, everything is going to be less than or equal to 2 to the power 32 minus 1. Because when you double a value, and it can no longer, the result of the doubling can no longer be stored in the 32-bit integer, C doesn't complain. C++ does not complain. It will just say, I'm just going to store the least significant 32-bit into the unsigned integer. Yes, there's one extra bit that is part of the result, but I'm just going to ignore that.
Can you compare it by knowing the actual number it is? Like if you know the greatest 32-bit number that can be represented,
okay,
you just compare and like flag it if it does.
All right, so let's look at the math. Okay, this is it boils down to algebra again. Don't you guys just love algebra? I mean, seriously, if you want to be a successful coder, developer, programmer, or software engineer, algebra is a starting point. Okay, you really got to know your algebra because you'll be working with values, and if you're working with values, algebra plays a really important part of how you can come up with the calculations. Okay, so the condition that we want to check is, can we double again? In other words, we are asking, if I double this again, is it still less than or equal to 2 to the power of 32, the whole thing minus 1? Now, remember, in your assignment, you're not going to use 32-bit, you're going to use 64-bit unsigned integers. So we're asking this question because if this is true, that means I can double x again, right? Does that make sense? The problem is everything is going to be less than or equal to 2 to the power 32 minus 1 because that is the maximum value that you can represent when you only work with 32-bit unsigned integers. Okay, let's digest that sentence just a little bit first. So let me take row first, okay? And as we digest that one sentence, and then we'll continue with this. So I'm switching to the browser to enable the row taking activity, and that is. I just need to go back one level. The vertical tab thing is really helpful, because I tend to have 30 tabs open in every single window. Um, so today is the 3rd of October. Today is actually, okay, so, okay, well, I'm going to write it on the board so when he comes back, he can see it too. All right, so I have changed, oh, you guys can see it from here too, but you will see it right here. So the access code is 52. It's not released yet, so don't refresh your browser just yet. I'll give you guys till 11:50. I mean, that should be enough time. And there we go.
It's a true or false question now?
Yes. But there's an access key to get in there. But the good thing is, if you type in the wrong access key, it will just ask you again. Instead of giving you typing in the wrong value, it will count you as a 0 instead.
It brings me back to your class last year when you used to type the answer in Discord, you explicitly say,
Well,
copy and paste.
yes. Well, in that class, I could copy and paste because we were using Discord. But in this class, it's harder to copy and paste from the whiteboard. I mean, you could. You can use, character recognition and then convert it to text and then you copy it. Yep.
Professor,
Yep.
for what you were asking earlier, since C++ doesn't check if it's up to 32 bits or not, could we explicitly represent that number with using a floor, or sorry, no, using float?
But we are not supposed to. So that's the whole point, because whenever you use float or double or any math related to float and double, it's very taxing to smaller processors. So if you have a processor that doesn't have a floating point unit, they really struggle whenever you use a math that involves floating points. Doesn't matter whether it's single or double, it's still very taxing. So I'm using only integers. So this way, this math can be done relatively quickly using a integer only type of processor. So I'm looking at it from the perspective of efficiency, given that you don't have the expensive hardware to do all the floating point calculations. All right, so we're getting back to algebra here. You just came back. Did you take a row? So you might want to do that because the access key is 52. You have until 11:50 to do it, so plenty of time. All right, so when you look at this comparison, a math professor would say, I don't see a problem with it. But that's because in math, there's no such thing as, oh, by the way, this, everything here can only be up to 2 to the power 32 minus 1. And then beyond that, we're using, guess what? Modulo, okay? Because all the math operations, when you're using 32-bit unsigned integer, all the math, division, addition, subtraction, multiplication, and whatnot, they are all using um, congruent modulo 2 to the power of 32 minus 1, which means everything is within this range. So a math professor would not see a problem in this, but I do, okay, as programmers we do. Well, but that's easy to fix because we can now say, that will fix the problem. Because now each, each side can only be within the range that we need to work with. There's no potential doubling of something that is already too big to be doubled. Is that okay? So now what do we get? We get x has to be less than or equal to 2 to the power of 32, the whole thing minus 1 divided by 2, which also can be expressed as 2 to the power of 32, the whole thing divided by 2, minus 1 divided by 2, which then translates to 2 to the power of 31 minus 1 half. So the question is, what is that minus 1 half going to do? Now we know that 2 to the power of 31 is going to be an even number. How do we know that? 31 looks odd to me, but what about 2 to the power of 31? It should be even, right? Because it's just a really gigantic product of 2 times 2 times 2 times 2 times 2. We just need 1 2 in the multiplication, right, for the whole thing to be even. Now we get like 31 twos. It has to be even. Okay, so we are looking at an even number, but the question is, if I use rounding, because remember we're using rounding here, this subtraction of 1 half, what is that going to do, when we want to actually look at the unsigned integer value as a result of that?
Round down.
It'll round down, exactly. So the whole thing becomes just this after rounding. Okay? So eventually what you're comparing, okay, ignore everything in between. So I'm going to circle the stuff that you can ignore. So everything from here all the way to here, you can ignore. Because it is just the end of one side we have the variable, the coefficient, and on the other side we have something that is clearly representable in 32-bit unsigned integer. So we just have to do this comparison. If it is less than, we can still double it. If it's less than or equal to, I should say, then we can still double. If it's not, you should not double again. Does that make sense? All right. So I'm just looking at the time here, and do you have any questions at this point about everything that we have talked about?
Can you go over the dividing by 2 again? Why that?
You mean this part?
Yeah.
The division by 2 is necessary because if you double x again, it cannot be represented using 32-bit. The comparison cannot detect it without okay, if it's just the original form like this, there's no way you can fail this comparison because everything as a 32-bit unsigned integer is guaranteed to be less than or equal to 2 to the power 32 minus 1. Is that okay? Maybe not.
I get but you divide it so that it fails? That's part of.
Okay, maybe I can illustrate it using a program. Give me a second here to set up the program. Because I think the question is the mechanism of comparison using 32-bit integers. So I think that's the question. So we're going to write a very simple program. Okay, I'm not even going to bother to save the program. We'll call it test again. So pound include stdint.h. This is where the uin32 underscore t definition is coming from. And then we got main. And we have two uint32 underscore t. I would just call one x and the other y. And we'll give x a particular value. Okay, it doesn't really matter what value we give them here because I can always change it in the debugger itself. All right, so that's the entire program. gcc-g-o test.c, gdb test. All right, put a breakpoint on line 9, run the program. I'm just using the program to give me two unsigned 32-bit integers. That's all I'm doing here. All right, so we're going to set x to be a particular value. So let's just say that x is the same x as in the comparison here. So I'm going to, oops, no. No. Okay, I just wanted to move this out of the way so I can show you the journal at the bottom. I know it's harder for you guys to see from the back of the classroom. Can everybody still see it? Okay. All right, so let me go back to the debugger, which is here. There we go. So we'll just set x to be something obvious and set y to be the largest value. So if x is so if y is supposed to be the largest value, which is 2 to the power 31 minus 1, how am I going to do it here? Because remember, I cannot do power. I cannot use the double function called power. There are several ways. I can specify that thing in binary, which is 31 ones. I can use 0t, I think that's base 2, and then try to specify 11 ones. Or I can also use my math here. So, okay, do you guys still remember the base 16 conversion stuff? A little bit, maybe. Okay. All right, so we'll answer one question at a time. We got time to do it. All right, so the first question is, okay, add a new page after. There we go. So the question is, oh, wrong color. Okay, there we go. So the question is, what is 2 to the power of 31 minus 1 in base 2? How do we figure this out? Well, 2 to the power of 31 is 1 followed by 31 zeros. Let me say that one more time. 2 to the power of 31 is represented in base 2 as one single 1 followed by 31 zeros on the right-hand side in base 2. So when you subtract 1 from it, then you end up with 30 ones, sorry, 30 ones entirely. Let me double check. Is that math going to work out? Okay. Because this is also the same as 1, left shifted 31 times, the whole thing minus 1. This is the left shift operation. So that means in 1 insert with 31 zeros on the right-hand side. That's one way to look at it. Okay? So that would be 2 to the power of 31, and then you just need to subtract 1 from it. So we're going to apply this in GDB. So y is going to be 1 left shifted 31 times minus 1. And now we're going to look at x. Okay, x is pretty easy. This is y. Okay, does that make sense to you? If I double this value, do you think it can still be it's still representable inside? That looks too small to me, because we can represent up to 4 billion something. So that means this is too small. There's something not right about my math here. 2 to the power 31. Oh, I forgot one shift. Because what? Okay, it should be this. Whoop, no. 2. There we go. I just spotted my own error. Okay, so this is correct. This is about 2 billion. Okay, and if you double 2 billion, you get about 4 billion, which earlier we said that's about the range of a 32-bit unsigned integer. So this is the right value. All right. So the question is, um, let's make y the largest value we can represent, which is um, one way to represent it is to say 1, 2, 3, 4, 5, 6, 7, 8. What is that? Okay. Do you guys remember what is 0x? It's a prefix for hexadecimal, which is base 16. And what is f in base 16? What is the bit pattern? What is the binary representation of the single digit of f in base 16?
All one.
All ones? Very good. Okay, good memory. So it's all ones, 4 ones, right? 1, 2, 3, 4, 4 ones. So how many ones are we specifying here? We have 8 f's. 8 times 4 is 32. And 32 ones as a base 2 number, don't you think that is the largest value you can represent using 32-bit unsigned? Because we have maximized every single digit in the entire 32-bit. Okay, so this is the largest. And we're going to set x to be about that, okay? So we'll say x is really close to that, okay? And then we ask, is x less than y? The answer is yes, okay? Not surprising because x is 15 less than y. They're both representable in base 16. So now I'm going to ask you another question. What about 2 times x is less than y? What do you think is the answer? If you ask a math professor, the answer should be no. Right? But if you ask the debugger, oh, it's supposed to be less than or equal to, but it doesn't make that much difference. The answer is, it is still less than. What is going on here? Because x is a 32-bit unsigned integer, so when you multiply that by 2, it becomes too large to be represented in 32 bits. So the resulting representation, which is the least significant 32 bits, is still going to be less than or equal to the largest value that you can represent using 32 bits. I can go step by step too. Okay, so let's go step by step, and we say what is x at this point. Okay, let's print x in hexadecimal. So we're going to say let's make it really really close. Okay, because I want to save us a little bit of time. So let's just make it 1 less than y. Is that okay? E is 1 letter earlier than f, so that's why this number is 1 less than y. So now we ask, is x less than y, less than or equal to y? The answer is yes. Okay. We say, let's make x equal to x plus 1. Okay. And then we ask, is it still less than y? The answer is yes. In fact, let's check what is x at this point. In hexadecimal, it's all f's. So x and y are indeed the same. And so if you ask if x is less than or equal to y, the answer is yes. What do you think is going to happen when we say, let's add 1 to x one more time? What do you think is going to become?
0.
Yep, exactly. It wraps all the way around to 0. So now the question is 0 less than or equal to 0x f? So this illustrates the problem that we have if we continue to use the 2x on one side of the comparison, because when we double x again and it's already exceeding out of the range, then we cannot detect it anymore. So without the division by 2, this will never work. So that is why. All right. So we are right on time in today's lecture. This stuff here is really important because on Thursday, you are going to get started with coding a little bit. Huh? On Wednesday, sorry. Yeah, on Wednesday. Keep getting myself confused, between this class and the other class. So on Wednesday, we're going to start coding. Okay, your so-called lab on Wednesday is to code and write the code to actually do the conversion. So you might want to um, bookmark the spreadsheet that I worked on earlier today. You can make a copy of that, and then you can just go like, okay, I'm going to modify this with a different value and just play with it. So if you want to do that, just go to File, and then you can go to Make a Copy. But when you do that, make sure that you change the folder first, because otherwise it will try to create it in the same folder, and it's not going to be successful because it is my folder. So when you use Make a Copy, the first thing you want to do is to go to Folder and make sure that you back all the way up to your own drive, Google Drive. Then you can go ahead and make a copy of this. And the idea of making a copy is you can now annotate it. Does everybody know how to use Google Sheets in a very basic way? So more or less, okay? So you can actually click on one cell, and then you can insert comment. So if you want to say, okay, I know something about this particular cell, it has a particular meaning to it, you just say insert comment, and then you just type it out, and now that cell is going to be commented. All right? So you really want to understand, okay, the first thing you want to do is to say tech gave us something that won't work as a condition. Change that first, okay? Change that to what I said earlier, divide both sides by 2, blah, 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 okay? And make sure that it's gonna work. All right, so we're out of time for the lecture, which is actually right on time for once. And I'm gonna release the lab for today now. So the lab today is kind of a continuation of the previous one. It still has a bunch of math stuff. So, but other than that, it's not too bad. Should not be too bad. Oh, here's the access code. So the access code to the lab is EXP or exponent, and I'll give you guys until 1:20 p.m. There we go, and off you go.